Reactions of carboxylic acids. As an acid, carboxylic acids can be reacted to a basic compound to produce a salt as the major product and water as a byproduct. Now, this reaction in general is known as neutralization or salt formation. You're all familiar with this reaction already, reacting an acid plus a base, that is neutralization reaction. For example, you have here a general reaction. You have any carboxylic acids given, a molecule which contains carbon double bond oxygen with a terminal OH, that is a carboxylic acid. Then it is being reacted to a base, sodium hydroxide. What happens here in the reaction is this carboxylic acid, as an acid, it will act, okay, as an acid, particularly via donating its proton. Recall, when we define an acid, it has the ability to donate a proton. So in the reaction, it will donate a proton, and as a base, sodium hydroxide will accept that proton. Okay. Therefore, in other words, base will be protonated here. All right. And this will produce a salt, specifically a carboxylate salt, in a form of sodium carboxylate, and liberating the byproduct water in the reaction. This is all about neutralization or salt formation, simply reacting a base compound to carboxylic acid, producing a salt, carboxylate salt, and a byproduct water. Next, carboxylic acids also undergo a specific reaction to transform itself into its acid derivatives. Recall, we have four acid derivatives that were discussed. Those are amide, esters, acid anhydride, and acid acyl chloride. Now, carboxylic acids, it is being converted to its derivatives via nucleophilic substitution mechanism. Recall that carboxylic acids, they contain a suitable living group. Okay? And that is in the form of OH. Thus, during the reaction, since it contains a good living group, this group, OH hydroxyl group, will simply be removed, okay, during nucleophilic attack. And what replaces the spot of hydroxyl here is the nucleophile being substituted. So that is all about the general mechanism of nucleophilic substitution reaction. Now let us start with the conversion of carboxylic acid to its acyl chloride equivalent. Again, we will be learning in this slide how do we convert carboxylic acid to its acid chloride derivative. Now to convert carboxylic acid to its acid chloride, you have to take note that the reacting reagent that you need to substitute is in a form of thionyl chloride. Thionyl chloride will be reacted to carboxylic acids, okay, producing a stronger nucleophile in the form of Cl, which will be then substituted on the carbonyl carbon upon removal of the living group hydroxyl, thus forming acid chloride. So this is simply substitution reaction. The hydroxyl here will be removed as a good living group. Then the stronger nucleophile that is being produced from thionyl chloride will then be replaced to the spot of hydroxyl. And you have here the byproducts. The most important thing here is the major product, and that is the acid chloride. So this is all about conversion of carboxylic acid to its acid chloride derivative. Let's have a specific example. For instance, you have here a benzoic acid. Now, benzoic acid, if you try to react that with a thionyl chloride, then you will produce benzoyl chloride. And you have here the byproduct HCl and sulfur dioxide. Again, the major product here is the benzoyl chloride. So the reaction only happens here. Okay, on the living group. The living group is just removed, and then the chloride that is produced, okay, the nucleophile in a form of chloride ion, it is produced from a thionyl chloride. Then it is the one that is being replaced with the hydroxyl group of the carboxylic acid. Next, let's have the conversion of carboxylic acid to its ester derivative. Now, to convert carboxylic acid to its ester derivative, the carboxylic acid has to be reacted to an alcohol. So this time, you will be needing an alcohol. So the um, general formula of alcohol is ROH. Whenever it is reacted to a carboxylic acid, you will then produce an ester product. And take note, whenever you react an alcohol to carboxylic acid, this is always be conducted in the presence of an acid catalyst. It could be sulfuric acid. Now, in the reaction, the hydroxyl group again, okay, this hydroxyl group of carboxylic acid, it will be protonated. So what is your idea? Whenever it is being protonated, the hydroxyl is being protonated, that this will be removed. This will depart, no, as a living group in a form of water. Okay, that is why you have here a byproduct in a form of water. It will be lost in the system in the form of water. Then what will be replaced in the hydroxyl of carboxylic acid? You will have there a stronger nucleophile from alcohol in a form of OR. Okay, recall whenever you react, okay, um, alcohol, okay, to a sample, okay, let's say it could be an aldehyde or a ketone, the nucleophile that is being produced out from that alcohol is the alkoxy. Okay, so the point of attachment is the oxygen of the alkoxy, because this is the one that is unstabilized, the one that is electron rich, right? So upon substituting on this part, then you will now produce then ester. All right. So that is how to convert carboxylic acid to its ester derivative. You will be needing an alcohol. The nucleophile that will be produced out from alcohol is the alkoxy. And that is the one that will replace the living group hydroxyl in the carboxylic acid. So let's have the specific example. Let's say you have ethanoic acid, or this is commonly known as acetic acid. Then it is reacted to ethanol. So again, uh, the alkoxy, okay, or the nucleophile that is being produced from ethanol is the ethoxy, the OCH2CH3. Okay, what happens here to the OH? It will be protonated. Okay, it will be removed. It will depart from the system of carboxylic acid in form of water. Then you will now produce the ester in the form of ethyl ethanoate. Ethyl ethanoate, or this is commonly known as ethyl acetate. Next, let's have conversion of carboxylic acids to its amide derivative. Now, the conversion of carboxylic acid to amide via direct, okay, reaction with an amine, okay, you have here any amine, this is expected to be somehow difficult. Okay, difficult to produce a product amide. This is because whenever you react amine to a carboxylic acid, of course, amine will act as a base. Okay, and again, amine is very much basic in character. So as a base, it will accept a proton. Okay, it will always accept a proton from carboxylic acid. So meaning to say, not the whole living group hydroxyl will be removed, okay, initially from the carboxylic acid. It will be deprotonated in order to donate, okay, that proton to a basic compound amine. Okay, it will be deprotonated to form here a highly unreactive carboxylate salt. So instead of forming directly an amide, initially this will produce a highly unreactive, non-reactive carboxylate salt in the form of ammonium carboxylate. However, whenever the salt, okay, ammonium carboxylate salt is being heated at an elevated temperature, at an extreme temperature, uh, let's say above 100 degrees Celsius, then what happens here is water, okay, water from this salt will be driven off. Water can be driven off because of this extreme temperature. And that's the time amide will be formed. Okay. But again, this reaction can be difficult to form an amide. Now, for easier way to convert carboxylic acid to its amide derivative, this can be achieved by first converting a carboxylic acid to its acid chloride form. Recall whenever we wanted to produce convert carboxylic acid to its acid chloride form, we will be needing thionyl chloride. Okay. Now, this acid chloride is more reactive. Okay. This is much more reactive compared to this ammonium carboxylate salt. That is why it would be a good idea to first form the acid chloride equivalent of carboxylic acid before reacting this to an amine. Okay, to an amine. Let's say the specific amine that is being added is ammonia, the simplest amine. Okay, let's say ammonia. Okay, this reaction will follow substitution reaction mechanism wherein this chloride group will be removed as a good living group, then what replaces there is NH2. Okay, NH2 producing an amide. Again, whenever ammonia is being added to acid chloride, then that will form an amide group. So let's have a specific example. Let's say you have benzoic acid. Okay. So initially it is being reacted with a thionyl chloride, so that will form a benzoyl chloride. Now, benzoyl chloride as an acid chloride, this is highly reactive. It can be reacted to an amine, thus producing benzamide. Okay. If I will try to draw this, okay, showing the carbon double bond O and then a terminal NH2, this is how to represent this. It's just the same. Okay. Next. The third reactions of carboxylic acid is what we call reduction. In general, when we talk about reduction, this is simply the mere opposite of oxidation. Okay. So meaning to say opposite of oxidation this time, this is all about addition of a hydrogen atom, removal of oxygen atom. So in the reaction, it uses a strong reducing agent. A good example of strong reducing agent is lithium aluminum hydride. This is a known strong reducing agent which can reduce almost any functional group into its alcohol form. Okay, again, it can reduce any carbonyl containing functional group into its alcohol form. Okay, so I repeat, during reduction, this is simply removal of oxygen. Now, let's say you have any carboxylic acid. Recall that this is a carbonyl containing functional group. Okay, and this part is the carbonyl group. As you can see, a carbon is doubly bonded to an oxygen. That would mean the component of oxygen, whenever it is being doubly bonded to an atom, that is equivalent to 2 oxygen. Okay, so whenever we remove, okay, oxygen here, we are actually removing two equivalent oxygen. Okay, during reduction, if we try to remove oxygen here, okay, on that the carbonyl oxygen, um, that is equivalent to two oxygen. So meaning to say, reduction here is simply removing the two equivalent oxygen in the carbonyl, adding then two equivalent hydrogen atom, okay, to that reactive carbonyl carbon. And as you can see, you are producing here a primary alcohol. This is a primary alcohol, okay? So again, what happens during reduction? On that carbonyl group, two equivalent oxygen will be removed. So ito mismo. That is equivalent to two oxygen. Yung double bond towards oxygen, you are actually removing two oxygen there. Okay, by theory. Removal of two oxygen, then in replacement, you have to add two equivalent hydrogen atom. That is all about reduction. Producing then the primary alcohol. So let's say, for example, you have a propanoic acid being reacted to a reducing agent, okay, very rich in hydrogen. So what happens here is remove, okay, that oxygen, then simultaneously here adding two equivalent hydrogen, producing primary alcohol, specifically propanol. Another example, you have benzoic acid. So removal of that oxygen on the carbonyl group, then simultaneously adding two equivalent hydrogen. So producing a benzyl alcohol. So we are done with the reactions of carboxylic acids. Now I wanted to uh, introduce one reaction among acid derivatives. So again, closely related to carboxylic acids are its derivatives. Diba? So when we say derivatives, again, these are the compounds in which the acyl, um, the acyl group, just like acid, um, the acid or carboxylic acid, okay, they are being bonded to an electronegative atom or a substituent that can act as living group. So the same with carboxylic acid. Acid derivatives also contains electronegative atom or substituents that also acts as living group during nucleophilic acyl substitution reaction. Now, there are actually many kinds of acid derivatives known, but we will be concerned only with the four mentioned early in the previous discussions. We have the acid chloride or acyl chloride. Another thing is the acid, let's say anhydride. This is acid anhydride. And then we have the ester. Okay, this is ester. And lastly, we have yan, amide. Okay. Now, generally, these acid derivatives, they undergo hydrolysis reaction. So I will just be introducing hydrolysis reaction among these acid derivatives. Okay, when I say hydrolysis, this is simply decomposition of a particular compound in the presence of water. So water is being used here, okay, to decompose, to break, okay, bonds in that particular compound, producing what is the product here upon hydrolysis. This will produce the original carboxylic acid compound. So, diba, as mentioned, these are derivatives of carboxylic acids. All of these compounds are only derived from carboxylic acid. So upon hydrolysis, okay, hydrolysis, this will simply produce the original carboxylic acid. Okay, so let's say they are being reacted with water during hydrolysis reaction. Okay, the final product here is ayan, major product is, of course, carboxylic acid. Okay, so this is carboxylic acid. Okay, specifically with, let's say, with acid chloride, number one, um, reacting that with water, okay, um, this will produce a major product, carboxylic acid, then a byproduct, HCl. Okay. Again, how this only follows substitution reaction. When we say substitution reaction, the living group will simply be removed. Then the hydroxyl, okay, from water will then replace the spot of that living group, producing carboxylic acid. Next, let's have acid anhydride. For acid anhydride, I have told you in our prior discussion that an acid anhydride, this is formed by simply combining two equivalent acids. Therefore, this will produce two carboxylic acids. All right. Next, with esters being hydrolyzed, okay, this will form its equivalent carboxylic acid plus the byproduct alcohol. Okay. And lastly, for amide, the byproduct here is in a form of gas, which is ammonia. Okay. So a gas in a form of ammonia. Arrow up, meaning to say a gas is formed. A gas is formed. Now, when we talk about its reactivity of these acid derivatives, the reactivity is most likely based on the electronegativity property of their substituents, okay? Particularly of this part, the electronegativity of their living groups, okay? That is the basis of their reactivity as acid derivatives. And it's based on theories, the higher or the greater its electronegativity of their substituents, the higher is their capacity to stabilize a negative charge, thus making it much more suitable living group. So kung they have a greater electronegativity property of their substituent, that would mean they would have, okay, greater or increasing reactivity towards nucleophilic substitution reaction.